Let's talk about resonance. Here is nitromethane again, but notice that the negative charge is on the lower oxygen and the upper oxygen is neutral. This isn't the only way to draw nitromethane. Here's another method. This time the upper oxygen is negatively charged, whilst the lower oxygen is neutral. They are resonance forms, also known as resonance structures. Nitromethane has two resonance forms. But how does this stack up against reality? Well, we know that a single nitrogen-oxygen bond is a length of 136 picometers, whilst a double nitrogen-oxygen bond is the length of 115 picometers. What do we see when we look at nitromethane? Do we see two discrete bond lengths or uniform bond lengths, whether we're looking up or down? What is that bond length? Well, the reality is that there is only one bond length, whether you're looking up or down, and it is 121 picometers. So in reality, there is neither a double bond nor a single bond. It's something in between, and that negative charge is being smeared over three atoms. Now, naturally, the nitrogen is going to have to contend with a full positive charge. And excluding this, oxygen is more electronegative than nitrogen. So oxygen would take more of the negative charge anyway. Now, remember that the nitrogen is more electronegative than a carbon. Let's look at a similar example. Here, you can see that we have replaced the nitrogen with a carbon. Now, organic chemists, as you might be getting an idea, are quite lazy. You'll notice I haven't drawn the letter C for carbon. This is intentional. It's the way we commonly draw carbon. We don't write the letter, we merely assume it's there if the line has changed direction and we haven't stipulated a letter. You'll need to get used to this abbreviation method. The functional group we will consider is called a carboxylate. Let's focus on the carbon and two oxygens, one with a negative charge. Now, this is one resonance form with the negative charge on the lower oxygen. But how do we convert this to the other resonance form with the negative charge on the upper oxygen? We do this by moving two electrons. They're marked as blue and red on the lower oxygen. We take them as a lone pair and convert them into a new double bond containing a pi bond between the oxygen and the carbon, where there was previously just a single bond. Now, there's something puzzling here. There is a change from 1- to neutral on the lower oxygen, but we've moved two electrons. That doesn't seem to add up. We need to think more carefully about this. One of those electrons remains associated with oxygen. When we start out, it's a lone pair on the oxygen. When we finish, it's part of the pi bond of a shared two electrons. One of them must be coming from the oxygen. Thus, it never moved from its association with oxygen, but just changed how it was deployed at the oxygen. The other electron, however, starts as part of the lone pair on the oxygen and ends as part of the pi bond, but this time we account for it as being associated with the carbon. And that one electron is how we are calculating the formal charge change of 1. But the negative charge doesn't rest on the carbon, because a second process that's the opposite of the first goes on above the carbon. Here we see that the double bond is being broken and converted into a single bond. Those two electrons are both being turned into a new lone pair on the oxygen. as one of those electrons in the pi bond was already associated with oxygen, there is no change in the atom it was associated with. But the other electron starts associated with carbon and ends associated with oxygen. Thus, a net change of one electron at the oxygen, causing it to have a negative charge. Now, mindful of organic chemists' laziness, we can't be bothered to draw all the dots for the electrons and depict an arrow for the movement of each electron. When we move a single electron, this is shown with an arrow that has a single barb. But where we move two electrons together, then there are two barbs to the corresponding arrow. So pay attention and look out for those barbs. By doing this, we can just draw one arrow to show the movement of two electrons. The arrow starts on the negative charge of the lower oxygen and ends in the middle of the single bond between the lower oxygen and the carbon. The second arrow starts on the middle of the double bond and ends on the upper oxygen. This is showing exactly the same process. But reality has to sneak in again. These resonance forms do not reflect reality. We know the length of a carbon-oxygen single bond in carboxylic acids, and it is 136 picometers. And the length of a carbon-oxygen double bond is 123 picometers. So here's the question. In reality, what's the actual length of a carboxylate carbon-oxygen bond? Well, it's 127 picometers. Whether you're looking above or below, it's the same length. This is analogous to the nitromethane scenario. We don't have a double bond nor a single bond between the carbon and the oxygen. It's something in between, and we are also smearing that negative charge across the three atoms. So none of them have a full negative charge, but they all have some of the negative charge, with more than a third of the charge being on each of the two oxygens. Neither resonance form actually exists. They are an extreme. So we don't have a full pi bond, and we don't have three lone pairs on an oxygen.